Yeah, the next speaker is Abdel Tawfik. I hope I pronounced this correctly. And his talk will be on the QCD phase structure in Polyakov linear sigma model with non-zero isospin density. Right. So can you share your screen?
Abdel, can you unmute yourself? I ask you to unmute. You should say yes, something like this. Yeah.
Ah, there he actually is. I was trying to find him.
You should, yeah, below at the bottom of your screen, you can see mute unmute button. Yeah. Now we can see your slides, and now you should unmute yourself. Yeah, you should. You can. Yeah. So just agree. I ask you to unmute. You should just agree.
Unmute, okay.
Yeah, okay. Yeah, you can turn on your video if you want. So, but
I'm online right now. Okay.
All right. Yeah.
Okay.
So
right. Thank you for the chair, and also I'd like to thank the organizer for inviting me to give this talk in which I'm going to review some of our recent results. I'm going to focus my talk on the QCD phase structure in the Polyakov linear sigma model with non-zero isospin asymmetry. My name is Abdel Tawfik. I'm from Egypt. I'm the director of the Egyptian Center for Theoretical Physics. I'm going now to give the agenda of my talk. First, I would give a very short introduction to the degrees of freedom in the linear sigma model, how we include the mesons, quarks, and gluons in this effective model. Then I will show you the Polyakov linear sigma model at finite temperature and baryon density. But for related to the topic, to my topic right now, today, I'm going to focus on the model at finite isospin asymmetry. Then I will summarize my results and conclusions here. This is a list of publications we have already done using this model. It covers a lot of things. I'm going just to review some of them. The talks is divided into two parts. The first part, I'm going to just review what we have done with this model. The second part, I'm going to focus on the finite isospin asymmetry and the results which we have obtained. Why we use a linear sigma model? Because it is a very economic alternative to the QCD simulation. When you are working in a country like Egypt, you don't have the possibility to run supercomputers and so on, then you have to use the effective model. Also, it gives us an alternative to the QCD. There is no need to invest a lot in having supercomputers. You can run your model using more conventional PHCs and also use very simple algorithm and programming techniques, which are enough together. But also this model, such model, also similar to the NGL or PNGL, enables you to study maybe the QCD phase change or phase diagram at higher densities, which is so far not possible in the lattice simulation. Various asymmetries in asymmetry breaking scenarios are also could be also studied. For instance, different properties of strong interactions, cohesion of state of hadron and particle matter, the chiral phase structure, and the meson masses. We have already studied up to 16 pseudoscalar scalar vector and axial vector mesons using this model. And we have studied the transport and the conductivity properties of the coefficient of the QCD matter using this model. Okay. The degrees of freedom in this linear sigma model, this is a low energy model, has generators TA, which connected to the Gell-Mann matrices and have a real classical field like this. The chiral asymmetry is explicitly broken through 3x3 matrix field. And you can see this expression where H is the external field in, of your interest. Under the chiral transformation, SU2 left, SU2 right, we get this transformation where this sigma A gets finite vacuum expectations value. This expectation value plays also rule of an order parameter in of the phase transition. Also, this finite expectations value leads to massive sigma particles and to some even light or even very massless Goldstone bosons, which are the ions. The original degrees of freedom of the model are the massless or the spinless, sorry, for this typo, spinless scalar sigmas field and the triplet pseudoscalar fields. Many properties could we study using the linearsigma model like breaking the axial anomaly, explicit symmetry breaking at non-vanishing quark masses, spontaneous symmetry breaking even through the chiral condensate. Okay. How we could include the quarks is very trivial. It just could be found in even in textbook. The QCD, the zero string interaction has some properties like this: asymptotic freedom, confinement, and some hidden breaking, hidden spontaneous breaking of chiral symmetries. Goes back to 18th of the last centuries when the quark are also included in the linear sigma model, the original one, where people already or colleagues understood that this model leads to describe the interaction of the quarks, and most importantly that the constituent quark gain masses like this, as m quark equals some coupling multiplied by the decay constant, the prime decay constant. Yeah, accordingly, the fermions could be integrated either as nucleon or as quarks. It has been shown that the chiral field transformation have the same behavior as that of the quark condensate, namely that the sigma order or the sigma coupling is a kind of order parameter describing the chiral QCD phase structure, and from the time we are using this model to study the QCD at the quark level as well. Also, we could include the gluonic degrees of freedom using the Polyakov loops or the Polyakov potential, where the chiral linear sigma model combined with the Polyakov sigma model, some expectations value of the colored Wilson loop at in time dimension read something like this, where this P of X are the matrix values of the Polyakov loop parameter in the basic transformation as given here. Here you can see the expression of this P of X. Another P here appearing as a parameter to the integral is order of the phase, the phase of the path integral when beta is the inverse of temperature. And this I'm showing you this how phi, the Polyakov variable, change with the temperature when also with the baryon chemical potential. You can see how sensitive are this phi to the different chemical potential, and also how this is changing with the temperature. Also, the degrees of freedom, as I said, the gluonic degrees of freedom, which are based on the Wilson loop, as I mentioned before, for which various parameters, for example, this phi and phi star, are given by this trace normalized to the NC, the color, the number of colors in your system. I'm going to maybe to skip this part and go to the Lagrangian of the system of the model. Lagrangian is simply consists of two parts: the color part and the Polyakov loop part. This color part combines also quark and mesons, where SU3 left and SU3 or both have SU3 left and SU3 right symmetry. For quarks, we have this expression for the Lagrangian. For mesons, we have this one. And for phi, or where phi in this exhibition are 3x3 matrix, including the non-net meson states. The Polyakov loop dynamics, which appears here as part of the Lagrangian, this could be modeled using recent lattice calculation or updated lattice calculation. For example, I'm just showing here one example for this, where we have different parameters here to be fixed using the lattice data. These are the suggested values of these parameters. Yeah. Accordingly, the model has different parameters like this Dirac, like mu and gamma and so on, which would also defined as a covariant derivative, and the Lorentz index, the chiral spinors, and so on. All these parameters have to be fixed before you can start your calculations. Okay, when you have done this, then you can write down your potential of this model. Okay, accordingly, we can use different approximation to deal with this model. I'm going just to skip the mean field approximation. It's a very trivial one. Then I can also I'm going to skip this optimized perturbation theory. There is no time to do this right now. Just I'm showing you the potential for two flavor. The potential reads something like this. Apart from the Polyakov and part from meson, and the third part from the quarks. And for issues for three flavors, we do the same, where the quark part also gains more degrees of freedom, more flavors like this. For 4 quarks, yeah, we modify the Polyakov part, the quark part, I mean, and the mesonic part. In all these expressions, the Polyakov part remains unchanged. Just to show you the part coming from for the SU4, you can see this. We are including the 4 quark flavors and the couplings, the condensates, the different condensate of the quarks, and so on. Sigma light, the condensate of light quarks consists or given in this expression. For the strange quark in this one, and for the charm quark, read something like this. With this, I just would like to see that we have a good control in our using our model, yeah, and the potential part coming from the quark anti-quark, we have expressed something like this, where you see this phi and phi prime and phi star, which are the Polyakov variable, as I have mentioned before. And you can see in this expression this the energy and the potential also normalized to the or as given as function of temperature as well. This enables us to study the thermodynamic potential at finite temperature and finite chemical potential. When we have moved from SU2 to SU3 and SU4, we have to follow this path as I'm describing here. We have to consider the symmetries for SU4, for example, and the part for the quarks reads something like this. Okay, for the mesonic part is this expression for the Lagrangian as well. Doing this, I can show you some results using the thermodynamic for SU4, for example, where here I'm just showing you the pressure normalized to T to the fourth, and so also the interaction rate normalized to the T to the fourth here, compared with the dots with error bars, which are the lattice results. Also, I can show you also the different condensates, the sigma light and sigma S and sigma charm, for and how they are changing or varying with finite temperature and also finite chemical potential as well. Expectedly, we see here these the Polyakov variable. They are changing with the temperature, but not too much with the chemical potential, at least with the baryon chemical potential. here are results for the thermodynamics, SU3 thermodynamics at finite temperature as well, and different chemical potential. And you can see using different approximations, the mean field approximation and the optimized perturbation theory approximation. Are some sensitivity we can study using the different approximations here. And here the bottom figure shows the comparison between both methods of calculations here. When I move to SU3 thermodynamics, here the correlations, the fluctuations, higher fluctuations compared to the latest data, you can see the good agreement with our calculation. I can skip also this one, which shows the product of higher orders, for example, kappa sigma squared, squared, and so on, compared to with our calculations, yeah. And also I can see also some, I can show also some correlations as well. When I come to the isospin asymmetry, I assume there as explicit symmetry breaking using the generator H equals TA, HA, where HA is a 9 parameter of the explicit symmetry breaking in SU3. As a result of the angular component of the asymmetry generator H0 and H3 and H8, which are finite in our case in this here and here. Additional to the mesonic field phi in 3 times 3 matrix, we have of the mesonic state, where sigma A and pi are the scalar and the scalar field. If we do this, this leads to some to an exact vanishing mean value of the of pi A, and to ensure that the mean value of sigma A, which corresponds to the angular generator of U3, as sigma 0 are not equal to sigma 3, not equal to sigma 8. Accordingly, we have now to estimate the corresponding variable for the isospin asymmetry. This leads me to say that the sigma 3 breaks the isospin asymmetry, and the potential which we have as purely mesonic contribution, like this. Sorry, I'm going back. Why? Okay. Here, just to write the U of sigmas like this, and the different parameters here are expressed in this very in this straightforward way, like this. Yeah, the explicit symmetry breaking terms H0, H0, and H3 and H8 can be determined using minimizing of the potential to the tree level. We have done this, for example. H3 and H8 can be determined using the partial conserved axial current relation, PCAP relation, like this. Where is this? It looks komisch. Okay. Here is the H1, H0, and H8 in PCAP relation are related to the pi mass and the decay constant of the pion and kaons of. This is our well relation. We are going to suggest and to introduce a similar relation for the isospin asymmetry in our model. And in doing this, and I'm almost running in time. In doing this, we have to derive the different constants, like the decay constant for pions, kaons, and even for K0. And we realized this, our results, we realized that sigma 3, which related to the isospin asymmetry, is given by the decay constant of Fk plus minus minus Fk0. This is our theory to estimate the PCAP for the isospin asymmetry. When we do this, we get something like this. This is our main result. H3 equals M A0 squared multiplied by Fk plus K minus minus Fk0. This is a novel version of the PCAP in which we manifest the sequence of the isospin asymmetry or finite isospin asymmetry, where the couplings, different couplings to the up and down and the strange quarks are related to the sigmas of 0s, 3, and 8 like this. And also the couplings are related to the quark masses using these expressions. Now, in order to determine the isospin, we have to minimize our potential. Just I'm showing you here results. Here are the couplings. There was a question about the couplings and whether they remain finite. In our model, they are not remaining finite. Here, they are changing with the temperature and changing with the isospin chemical potential like this. Here we start with 0 isospin chemical potential. This is normally we cannot distinguish between the light strange and condensates. But if we increase the isospin chemical potential here to 50 MeV and here to 100 and so on, we see a very distinguishable difference between the three condensates. Here I'm showing the Polyakov variables as function of temperature and various chemical potentials 0, 50, and 100. There is a little change, very insensitive to the change in the isospin chemical potential. But if we change it, we study here the isospin chemical potential as and how this affected the Polyakov variable, we see here differences which are distinguishable. Here are the QCD thermodynamics at finite isospin and temperature, of course, and we are comparing our result to lattice. We see the good agreement here for the pressure, and here we just varying the isospin chemical potential. This is our expectation for the lattice studies for the pressure at finite different isospin chemical potential. Here's the interaction rate at 0 isospin chemical potential compared to, and here also our expectation at finite isospin. And here I move to the fluctuations. Here for the baryons, and here for the electrical charge, and here for the isospin, I think, for the isospin here. And we compare our results with the lattice, and here our expectation are given in the right-hand panel of our graph. Here I'm just showing you again the fluctuations at different varying different isospin chemical potential. Here at 0 chemical potential compared with lattice, we can see the excellent agreement, and here at expectations at finite isospin and so on. Now I come to my last slide. Here is the QCD phase diagram at finite chemical potential. Here we study the critical temperature, or the temperature normalized to the critical one at finite isospin chemical potential compared to different lattice simulation, and you can see the agreement in this way. I think we have a good agreement here. Our conclusion is that we have used a linearsigma model. We included various degrees of freedom, mesonic and quark, and even clone degrees of freedom. We have studied SU2, and we extended the model to SU3 and even to SU4 as well. We also included temperature, baryon chemical potential, magnetic field, and isospin chemical potential. We have studied up to 16 meson state at finite temperature, baryon chemical potential, and even magnetic field as well. We also have studied, maybe not published, not illustrated here, but I mean in general, studied the viscosity and conductivity at finite temperature, baryon chemical potential, and magnetic field as well. The thermodynamics and the higher order fluctuations as well. In this talk, I have shown you the QCD phase diagram at finite isospin chemical potential. I still have time for if you have any question. First, let me thank you very much. Thank you.
All right. Yeah. Thank you for your talk. Well, the last words I somehow didn't hear very well. There was some, but that was just the last few words. That's why I hesitated to step in. All right. Thanks a lot. Yeah. thanks again. And are there questions? Right. So no one seems to have any question at this point. So could you show these fluctuations again once more, maybe?
Fluctuations.
I was not sure. I was getting. You were quite quick at that point, so I.
Is this one you mean?
I'm not seeing your screen anymore. Could you? You stopped sharing. Could you share
Yes,
again?
I didn't. But I can try again. Right now, share. Can you see my screen?
Yeah, now we can see it.
Okay, is this one? What did you mean?
No, actually you had a plot where you showed the fluctuations at non-zero isospin, right? Is this?
Okay.
Well.
Maybe I can start.
No, this is not what I had in mind.
Maybe this one's.
Right. Exactly.
No, the thermodynamics. Here's the chi's different. Let's see, chi square.
No. The previous plot was the first one. I was just trying to get what was on this plot. And no, what you had before. I'm sorry for the confusion. The one that you showed was right. I was just trying to get.
Okay, this the chi square. You mean? Okay.
Yes, in principle that. There's also a question by Gary. I will come to that in a second.
What is it?
Could you?
Yeah.
No.
Not this one.
Not well, the other that you showed, where it is calculated at finite isospin chemical potential. I think. This one, I think.
Okay, fine.
Let's have a look here.
Yeah.
So yeah, I first wanted to have a look, but then also Gergo has a question. So please, Gergo, ask first. I'm chair. So
So I just wanted to make sure I understand it. Do you also consider the possibility of pion condensation here when you crank up the isospin chemical potential? For example, on your last slide with the phase diagram, I somehow had the feeling that
yes. We have taken this into consideration. I think we have used your values, Georgi.
Mm-hmm. I'm just wondering if you can take into account pion condensation in the model consistently.
Yes, we have done this. We have done this already, but we didn't publish. I mean, we didn't publish a paper explicitly on this, yeah. But we have taken this into consideration, and we have included this in our calculation at least. But we didn't publish because we didn't think that this could be enough for a paper alone, yeah. But we have already the calculations. I mean.
Okay, I see.
Yeah.
And is there any interesting thing to learn from how you include pion condensation in the linear-sigma model?
Yes, of course. At least I mean, we are in good agreement with your calculations that there are some limitations. For example, we couldn't have the pion condensation at lower temperature. Only the isospin chemical potential start from a finite value of the pion mass and so on. This is what we have already obtained.
Okay, thank you.
Yeah.
Mm-hmm. All right. Yeah. So thanks for the question and the answer. I also just saw I was wondering about the point on the right, but then I saw that you start at 0.5 t. So I was wondering why this doesn't go to 0, but yeah, of course.
Okay,
I understand it perfectly fine. I was mistaken. I was
okay, fine. Very well.
All right. So is there actually any other question, or was that basically it?